Do you know the work energy theorem or the total mechanical
Yeah,
energy theorem? Okay. See,
yeah,
this question is saying that you have a spring and you have a slider. The initial mass of the slider is 30 gram and it is at rest, so u is equals to 0 initially near the bottom of the frictionless slope, so its friction coefficient is 0, and in contact with a light uncompressed spring as shown in the figure. The spring is compressed by 5 centimeters, so this is compressed by 5 centimeter, and the slider remains in contact with it. The spring is released and causes the slider to rise up the slope to a maximum vertical height of 20 centimeters. So initially its vertical height was 20 centimeter. After releasing, the question is saying that the slider is replaced with one of the mass 20 gram. Now the question is saying that this 30 gram gets changed into 20 gram. The spring is now compressed by 15 centimeter. This 15 centimeter gets changed by this 5 centimeter gets changed by 15 centimeter, and the new slider remains in contact with
yeah.
T. To what maximum vertical height does the new slider rise after release? So it wants to ask how much final height it will get. Yeah, please tell me. Have you any idea how we can attempt this question?
We can find E equals fx, half
E
fx.
is equals to half fx square. Okay,
No square.
is equals to half fx, right? Very good. Yeah. Then
Then you can substitute the height energy as potential energy, so it will be zero
m.
point 0.5.
Okay, just do your method. Can we conserve the mechanical power here? Can we apply the conservation of total mechanical energy? Initially should be equals to total mechanical energy finally. Have you heard this?
Yeah,
So initially, before just the releasing, our spring potential energy was half kx square, isn't it?
yeah, yeah,
Plus no gravitational potential energy, that is the 0, plus no kinetic energy because it is starting from the rest, isn't it? So kinetic energy
yeah,
also 0. But at the end point here, finally, what will happen? No spring potential energy, that is the 0. No kinetic energy because here again it will come into rest, right? So potential energy also 0, and the potential energy will be mgh, isn't it?
yeah,
So we have half, we don't have the k, we have the x. Initially my x was 5 centimeter, so I should write 5 upon 100 in proper unit, meter square, should be equals to m
yeah.
is 30, so we should write 30 upon 1000 kg. G is 9.8, or we can take it 10 also, I think 10. Okay,
Yeah. Can
okay, keep it 10, keep it 10 into h is 20 centimeter, I think. Yeah, 20 upon 100. Can you find k from here? Please find k.
48.
48, right? Now similarly do the
Yeah,
same thing for the second case. What's the second case is, so in the second case I should have half kx square, that is the compression. Potential energy will be 0, kinetic energy will be 0. At the final point I will have spring energy 0, kinetic energy will be again 0, and now I will have mgh dash, that's the maximum height. So now you have the k, you have the x, so it is half, k is 48, x is what, x is now 15 centimeter, so I should have 15 upon 100 whole square, that should be equals to mass is now my 20 gram, I think. Yeah, so 20 upon 100, g is 10, sorry, 20 upon 1000, g is 10, and this is the h dash. Please find h dash from here.
27. I got, yeah,
Correct?
270. Yeah,
Correct. Now see, you can
yeah.
minimize this solution also. If you think, we can minimize this solution also. You know how? Even without finding k we can do this. See, total mechanical energy initially should be equals to total mechanical energy finally. So write the expression. So initially it
Yeah.
is half kx square plus potential energy, gravitational potential energy will be 0, kinetic energy 0. Finally, I have potential energy as mgh, spring potential energy will be 0, kinetic energy will be 0. So what's the expression I am getting? Half
Yeah.
kx squared is equals to mgh. Now I got my error initially. Okay, so now without finding k, you can calculate your answer. See how? Now you have two situations. The first situation for different condition, and the second situation. So if you take the ratio, so what I will write, half k will be the same for both, x1 whole square upon
Yeah.
half k x2 whole square. Are you getting? This is the first case I'm assuming, and this is the second case. All the information related to first and second. That should be equals to m1
Yeah.
g h1 upon m2 g h2. Can we do this?
Yeah.
Very good. See, half gets clear, k gets clear, g gets clear. So very simple relation now I will have x1 upon x2 whole square should be equals to m1 upon m2, this one, into h1 upon h2. In this method we have one another advantage, that we don't need to change the ratio units. We will not need to change the units. No, why?
Yeah.
Because they are in the ratio form now. So x1 initially how much compression was? Initially 5 centimeter. So just write it 5 centimeter. Later in the second case it is a 15 centimeter. I do not I will not change the unit here. So this is the square m1. Initially how much? It is the 30 gram, I think so. Then it is 20 gram. So
Yeah.
write it 30 gram and then write 20 gram. Initially how height was 20 centimeters. You don't know the final height, so let it be h2. See, centimeter cancel out, gram cancel out, so it is 3. So it is 1 by 9. It is 1 by 9 is equals to 3 by 2 into 20 upon h2. So you can cancel it by 10 times. So h2 should be equals to 270. We are getting directly, quickly and precisely. Yeah, any doubt?
Yeah.
So see, in this manner
No.
we are avoiding the finding of k, we are avoiding the unit conversion, and that's the concept here. And I think you know why I have applied here total mechanical energy conservation, because there is no any
Yeah.
uh, non-conservative internal force and there is no any external force. So in this case my total mechanical energy will get conserved. Yeah, is it okay?
Yeah.